Today, we'll try to discuss about the transient response of a series RLC circuit with a DC excitation, where excitation is called input using an Laplace transform method, where this Laplace transform method is also called S domain. So S is equal to j omega and omega equal to 2 pi f, and this is also called S domain, or this is also called frequency domain analysis. Okay, let us try to handle this derivation. So this is like solving the equation in a simplified manner. So the resultant equation, what the transient current we will be getting, it is some constant k1 into u to the power first root plus constant k2 into u to the power second root. So why we got two roots is we have two energy storage elements L and C. So it's very simple. So already I told transient response means this is present for smaller duration. For example, you have been turned on a fan. Okay, so this is nothing but current in the fan, and this is nothing but the time. Just you have been turned on the fan. It takes some time. It oscillates and it will try to come to reach the required speed, and it reaches the required speed of 1500 rpm. As soon as you turn on the fan, it starts moving from 100 rpm to 100, 300, 400, 1000, 1200, 1300, and it reaches for the time taken by the fan to reach its required speed. What is the time taken by the fan to reach its speed? It's only 4 seconds, or approximately it will be 4 times the time constant. Therefore, this interval or the short interval, it reaches to the steady state, is called as transient state, and this is present as 4 times the time constant. 4 into 1 second, which is equal to 4 seconds. Okay, so try to come to a clarity. Transient means a sudden change, and the sudden changes or sudden disturbances are present for lesser duration. In this lesser duration, how our network is responding, what is the type of current, how the current nature of current is, we are going to discuss here, which is a very much important derivation while solving the problem. And the transient response of the series RLC circuit. We are going to take a series RLC circuit, and we are going to give a DC excitation by solving. So we are not solving by conventional time domain analysis. We are using Laplace transform analysis. Okay, let's try to solve the problem. So coming to the derivation, we are going to have a voltage source V, and we are going to have a switch, and the switch is opened at interval t minus, and it will close at t plus, and you are going to have a resistor, and you are going to have a inductor, and you are going to have a capacitor. So this is in which domain? Time domain. So here the resistance offered is R ohm, the inductor is L Henry, and the capacitor is C farad. So this is in time domain. You can use time domain method, which is a lengthy process. So for simplifying the calculation, I am transforming this network by applying Laplace transform, and I am expressing in S domain. So here you are going to have a voltage source. So Laplace of a constant. Laplace of a constant is 1 by S. This is V by S. And here you are going to have, you can see here, this is the network and t less than 0, and this is the nature of the network at t greater than 0. When t is greater than 0, the switch has been closed and the supply is available. This is nothing but indicated by short circuit. You are going to have a resistor, you are going to have a inductor, and you are going to have a capacitor. Okay, so the resistance of this is R ohms. So this is nothing but L Henry. So multiply that L with S, you are going to get SL ohms. Multiply this capacitor with S, C, and perform inverse of this, you are going to get ohms. So now I transform resistor, inductor, capacitor into an format of S domain. So here you are going to get the current, which is nothing but I of S. So whenever the current is entering, this is positive, current is leaving is negative. Whenever the current entering is positive, current leaving is negative. Whenever the current is entering is positive, current leaving is negative. So let's try to apply Kirchhoff's voltage law inside the loop. When you apply the Kirchhoff's voltage law inside the loop, so here you are going to get positive, negative. The current is leaving. What is the leaving polarity you are going to have? Which is nothing but V by S, and it is entering at positive terminal, and the current is leaving. What is the leaving polarity of the voltage? Minus I of S into R, and the current is leaving. What is the leaving polarity of the voltage? Minus I of S into SL. So it is nothing but voltage. So IR voltage, IR voltage, and here once again you have a capacitor minus I of S into 1 by SC ohms, that equal to 0. So this is nothing but application of here. This is voltage source. All these are voltage drops. The algebraic sum of voltage sources minus voltage drops is equal to 0. So here you are going to get it as so I'm shifting all the negative terms to the right hand side, and I'm taking I of S as common. When I take I of S as common, I'm going to get R plus SL plus 1 by SC. So this is what you are going to get, but we require the expression of I of S. Okay, so therefore the expression of I of S is equal to V by S divided by R plus SL plus 1 by SC. So here we want to make the coefficient as 1. So what we are going to do here is we are going to take the LCM. So when you take the LCM, you are going to get the LCM is SC. So this is R SC. SC into SL is S square LC plus 1 to the V by S. Okay, and you can see here S will get cancelled, and we can write down this as V divided by, so here I want to make the coefficient of S as 1. What I can take common? RC as common. So RC divided by C. So CC will get cancelled. So when you divide with RC, you are going to get S plus S square LC divided by RC plus 1 by RC. We are going to get 1 by RC. Okay. So this is what the expected expression we are going to get. Let's try to solve it further. So when you see this equation, here also CC will get cancelled out, and here you are going to get V divided by, so this is R by 1, this is nothing but 1 by R, I mean V by R, and here you are going to get, so here also, here you have the expression of S square. Okay, so better you can take LC as common. Okay, so why? Because here it is S is 1, so see here, don't do this as common. So here we will make the coefficient of S square as 1. Okay, so how to make the coefficient of S square as 1 is, so V by S divided by, so here I want to make the coefficient of S square as 1. I am taking LCS common, which is nothing but S square plus R SC divided by LC divided by 1 by LC, and this is already having the term C. So CC will get cancelled automatically. You can see here. So this can be expressed in this format. So which is nothing but V by S, this is nothing but 1 by L divided by, so this is 1 by S, when it comes to the numerator we are going to get S into S square plus S into R by L plus 1 by LC. So this is what the expression we have been got. Now let us try to solve this expression. So what are the units of this equation is? So let us try to solve it. So here S also will get cancelled out, and ultimately you are going to get V by L. So the ultimate equation after solving, you are going to get it as V by L divided by S square plus S into R by L plus 1 by LC is the utmost equation up to now you have been derived till it. So don't get confused like this. Making coefficient of S as 1, better you make the coefficient of S square as 1, then it will get simplified more. So this is an second order expression. So when you come to this second order expression, so this is in the standard format, S square plus S into R by L plus 1 by LC. So this is an S square. How many roots are possible? The first root is S1, the second root is S2. So this is in the standard format, AX square plus BX plus C. So what are the roots of a second order equation? Minus B plus or minus root of B square minus 4AC divided by 2A. So here, what is the coefficient of this? B value is minus R by L plus R minus B value is R by L whole square minus 4 into A value is how much? It's nothing but 1. So here, what is the A value? It's nothing but 1 into C. C is nothing but 1 by LC. So here you are going to get the two roots. So these roots I am going to call it as S1 is the root minus R by L plus R minus root of R by L whole square minus 4 by LC is the first root, and similarly S2 is equal to minus R by L minus of same root of R by L whole square minus 4 by LC is the second root what you are going to get. So this is the first root and this is the second root. So from these two roots we can write down this as so I of S is equal to what is the standard form we have? V by L divided by S square plus S into R by L plus 1 by LC. This you can write down it as V by L divided by, so you can write down this as divided by S minus S1 is one root, and next one S minus S2 is the another root. These are the two roots which are possible. So this you can solve it by partial fraction, which is A divided by S minus S1 plus B divided by S minus S2. So when you solve it, the LCM is S minus S1 is the one root, S minus S2 is the another root. You are going to get A into S minus S2 plus B into S minus S1. Okay, so here you have these two terms will get cancelled out. Substitute S is equal to S1. When you substitute S is equal to S1, automatically this B term will become 0. So let us substitute S is equal to S1. Substitute S is equal to S1, the term we are going to have V by L. S is equal to S1, we are going to get A into S1 minus S2. So therefore, A equal to V by L S1 minus S2 is the one unknown constant. Similarly, substitute S is equal to S2. When you substitute S is equal to S2, this term will become 0. V by L is equal to B into S2 minus S1. Now what is the value of B? B equal to B by L into S2 minus S1. Now substitute these values in this above expression. Therefore, I of S is equal to V by L S1 minus S2 divided by S minus S1 plus B value is V by L S2 minus S1 divided by S minus S2. Okay, so here this is very simple to understand. So this I am assuming it as a constant of K1 and I am assuming this as a constant K2. So I can write down it as I of S is equal to K1 into 1 by S minus S1 plus constant K2 divided by 1 by S minus S2. So this is in frequency domain. Apply inverse Laplace transform. Therefore, you are going to get I of t equal to K1. So L inverse of, when you apply inverse Laplace, 1 by S minus A is equal to e to the power at. Okay, so here we are going to get e to the power s1 t plus k2. Here you have negative, automatically you get positive e to the power s2 into t. So this is what the expression of I of t. So derivation is more lengthy but very important when you are solving in an exam. Okay, so we just try to review. We convert the time domain into frequency domain and we try to apply a small KVL and we derive the expression of I of s, and in this expression we want to make the coefficient of s square as 1. So that's why we have taken coefficient of s square as 1. That's why taken LC as common. We have made this automatically. You can see this expression. Here we are having v by s. Okay, so automatically the s also will get cancelled out, and resultant equation is v by l into s square plus s into this, nothing but a second order equation, and a second order equation will have two roots that we are writing it as s1 and s2, and we are expressing this in the format the two roots as s minus a and s minus b, that a is nothing but s1 and s2, and we want to solve this. That's why we applied the partial fractions method, and we have find the unknown constant a and b and substituted in this expression. We have got the k value is v by l into s1 minus s2, v k2 is v by l s2 minus s2. So this is what the transient current, or this is called the transient response of a series RLC circuit. We are solving it in which domain? S domain. If you feel the video is very useful to you, please give one like. Please share with your friends those are studying this content, and subscribe to the channel to have more videos. And if you do all these three things, which will be a support to the channel, and we can do more, we can put more efforts, and we can also grow, and we can make you also to grow by giving you more knowledge. Thank you for watching the video very patiently. Yours obediently, Ram. Thank you.